In this video, we are going to work through 5 examples of writing direct proofs of an implication of the form P implies Q. The first 2 examples are fairly fast, and I expect everyone watching this to be able to follow the math involved. In particular, with 1 and 2, what we are illustrating is what it looks like to check that a definition is being satisfied. And then example 3 is also something I think everyone should watch. This is the triangle inequality. And it's actually a very important inequality in mathematics. I will prove this 2 different ways, and one of the ways that I prove it will be a proof by cases. So not only are we going to cover direct proofs, but we are also going to show what it looks like to break up a proof into cases. And then just to be very thorough, mathematically, 3 will generalize to 4, so 4 will be a quick follow-up to number 3. And then in example 5, which involves a statement from linear algebra, I'm going to show what it looks like to take a definition, understand what it means, and extract a property from it. So that is the goal of these 5 exercises: check definitions, proof by cases, as well as talk about some important math inequalities, and then take a definition a bit further than it appears at first glance. All of these will be direct proofs. So a direct proof is where you literally start with the hypothesis P, do whatever mathematical operations you can with P, and arrive at Q. So when you read a direct proof, the flow should follow the flow of the original implication. From the hypotheses, we move to the conclusion Q. Now you might notice that 1 through 4 are not written as if-then statements. So the first step in each of 1, 2, 3, and 4 will be to clearly identify what the hypotheses and conclusions are. The first statement we want to prove is that the sum of 2 odd integers is even. This is stated like a fact, but we need to recognize it as an implication. So my first step is to rewrite this as an if-then statement. All right, what's happening here is we're taking 2 odd integers, we are adding them together, and we are observing that the result is even. So our hypothesis will be if m and n are odd, okay, that's what we start with, then m plus n is even. Is even. I think this is always the first thing you should do with a statement like this, is recognize what your hypothesis is and what the conclusion is. So this is what I would think of as the statement P, or the condition P, and this is our conclusion Q. That was the main observation to make with this first example, but now we are going to prove this statement. What I would like to do for most of the proofs in this lesson on proof writing is start by showing you the kind of scrap work that I would do on paper off to the side before I write the formal proof. So let me label this scrap. And this is like your brainstorming session where you see what you are able to do with the hypothesis. So it's not going to be full sentences or anything like that. I'm just going to imagine that I'm kind of playing around with the ideas in the statement P here. Okay, so we know that odd integers can be written as twice another integer plus 1. So let me imagine m has this decomposition, and likewise the odd integer n is, say, 2k plus 1, where j and k are integers. What happens if I add them together? I get m plus n, and then here I will have 2j plus 1 plus 2k plus 1. We recognize that's 2j plus 2k plus 1 plus 1, so plus 2. I will stop my scrap work there, but hopefully you realize the next step will be to factor 2 out of this and realize that the sum, m plus n, is twice an integer. So now I've seen that I can start with the hypothesis P, the hypothesis, and arrive at the conclusion Q. If you can do that, then you have a direct proof. So in a moment, I will come back and write up the proof itself. the proof we are about to write, being a direct proof, will mirror the statement here. So we will open by presenting our odd integers, and we will conclude once we've shown that their sum is even. I like to open my proofs with PF, or the word proof. You don't want to just jump into the middle of a proof without introducing all of the pieces that you're going to use. It can be concise, so I'm just going to write, suppose M and N are odd. Now I'm going to bring in that decomposition we just had. The fact that M and N can be written a certain way is the definition of an odd integer, so I'm going to mention that this comes from a definition. By definition, or to be more specific, by the definition of odd integers, I will use a quantifier here. There exist j and k from the set of integers such that m equals 2j plus 1 and n equals 2k plus 1. All right, so I've introduced m and n, and I've introduced j and k. I didn't just start using them without saying that they are themselves integers. Consequently, the next mathematical computation I'm going to do is both long enough and important enough to kind of merit its own line. So I'm going to say down here, m plus n equals 2j plus 1. How about I write 2j plus 1 plus 2k plus 1? And then I'll say that that is 2j plus k plus 1. It's a little hard to tell when I write on this board that I intend for this to be kind of in a paragraph and this to be centered on its own line. I hope that structure of the proof comes out. All right. I put a comma here because I'm about to write which is even. I'm not going to be so pedantic that I'm going to explain that j plus k plus 1 is an integer. Integers are closed under addition and closed under multiplication, and in most mathematical contexts, you would assume that. Okay. All right, so we have an even integer. I don't want to write a huge conclusion. When you have a direct proof, because the structure of the proof follows the structure of the statement, you can usually wrap these up pretty quickly. Thus, m plus n is even. All right. Let me make a few remarks. I'll step away so that you can read this, and then I'll make maybe a few more remarks. I open with the word proof, abbreviated as PF. I close with this box. That's what I like to do. You might have a slightly different way of starting and ending your proof, but I think that you should have kind of markers saying where the proof starts and where it ends. It helps the reader. I also want to mention that whenever you're working with variables, kind of named quantities in a proof, don't make the reader deduce what they are, introduce them. So here I've said M and N, I've brought them in. Likewise, J and K, I brought them in a way that didn't make the reader kind of figure out, oh, she's working with odd integers, you know. All right, I'll step away so that you can read this. The other thing I will mention before we look at number 2 is I'm not completely happy with my conclusion sentence here. Sometimes you make edits after you write a proof. So one thing I could have written instead is, thus, the sum of two odd integers is even, something a little bit broader that doesn't stick to the usage of m and n. Another thing that I like to do when I realize I've reached the conclusion and I believe the reader has reached it along with me is actually just write as desired and kind of avoid like a long conclusion statement. Our second example is phrased very similarly to the first one. Take a moment to pause and rewrite this statement. The product of two rational numbers is rational as an if-then statement so that we can clearly identify the hypothesis and the conclusion. All right, the heart of this statement is that the product is rational, so that's where we recognize the conclusion. The hypothesis is that we have two rational numbers to start with. So I will write if A and B are elements of the set of rational numbers, so that's what that notation means, then AB is a rational number. So then AB is also an element in the set of rational numbers. Once again, let's do some scrap work. There is a definition for rational numbers. A rational number is a ratio of integers. So 3/7, for example, is a rational number. So for my scrap work, I'm not going to write out any words or anything like that. I'm just going to imagine that A has been written as a ratio of integers. So how about P over Q? P can be any kind of integer, including 0. Q cannot be 0. Likewise, B will be R over S, where S is non-zero. Given that I now have forms for A and B, we can compute their product, PR over QS. Integers are closed under multiplication, so the numerator is an integer, the denominator is an integer, and then since neither Q nor S is 0, their product is non-zero. So I think we're good to go. You can, if you'd like, pause and write out the proof. It should only be a few lines, and it should be sort of similar to the one that we just worked through. I will come back in a minute and do it as well. Like before, this is a direct proof. So the flow of the proof is going to follow the statement here, this if-then statement. Let me start with PF in my usual way. Suppose that A and B are rational numbers. Right, now let me bring in that form for rational numbers that we just worked through. Then there exist P, Q, R, S from the set of integers with the two denominators Q and S non-zero. I think no comma here. So that A is P over Q and B is R over S. Thus, AB is PR over QS. I'll put this in a, well, I'll just keep going. Notice PR and QS are integers. And we really need to point out that QS is non-zero. Don't skip that. Make it explicit for the reader. I think stating it is enough, but if you'd like to, you can mention it's because neither Q nor S is 0. No long conclusion here. We have expressed the product, AB, that we were interested in as a ratio of integers, so we're done. I've already used the word thus, so just for some variety, I'll say hence. Okay, so the product of two rational numbers is rational. I think we are done with this exercise, but if you'd like to, you can work through a similar exercise showing that the sum of two rational numbers is rational. Take a moment to read this statement and identify the hypothesis P and the conclusion Q. When we come back, I'm actually going to start writing a proof right away. So you could also take some time to play with this inequality, try it on a few different numbers if you like, do a little bit of scrap work before seeing me write the proof. This statement is not being given to us with the language of if then. So let me identify it. For all real numbers a and b, the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. Again, it feels like a fact, but it's an implication. And how I'm going to present this hypothesis is, instead of saying for all a, b, and r, let's just say if a and b are real numbers, then the inequality. Okay. So our hypothesis is that we have two real numbers. We want to show that the inequality holds. I'm going to do a bit of brainstorming out loud. This might be what you arrived at in your scrap work if you experimented with this inequality. What matters when you take the absolute value of a real number? The sign of the absolute value. If you take the absolute value of a positive number, it feels like you don't do anything. So the absolute value of 5 is just 5. On the other hand, if you take the absolute value of a negative number, there's an action you have to take. You flip the sign. So the fact that we proceed differently with absolute value computations based on what we're taking the absolute value of might lead you to want to handle this inequality differently for, say, positive numbers, negative numbers, and that's the first version of the proof I'm going to do. So I'm actually going to prove this twice, and the first one is going to be what we call a proof by cases. We will show this with cases. So a proof by cases is where you are trying to prove a global statement, and what you do is basically divide and conquer. So trying to address all pairs of real numbers at the same time is tricky because of the way the absolute value behaves. So instead, I'm going to take my hypothesis and break it into different cases so that I can really specifically identify what happens when we compute absolute values. All right, there are different ways that you could do this, including considering every possible way that A and or B could be negative. So you could break it up into several cases, but there's a really nice way to break it up into just two. So my first case will be to imagine that the sum of what's inside here on the left, A plus B itself, is non-negative. I am going to use a fact throughout this proof. So I'm going to write it down explicitly for the reader now, which is recall that the absolute value of a number is always greater than or equal to the original number, or the way I'm going to order it is actually the opposite inequality. So recall that any number A is less than or equal to its absolute value. So this inequality is true for all real numbers A. And you can just quickly test that. So 3 is less than or equal to 3. Negative 3 is also less than or equal to 3. I'm saying recall here because if you've seen the definition of absolute value, you can make this observation. So I don't want to act like I'm kind of referring to something obscure here. That's my usage of the word recall. Okay, moving along. We find centered on its own line, because this is somewhat lengthy and it's also important, I'm going to take the absolute value of A plus B. Since I'm taking the absolute value of something greater than or equal to 0, it is simply what's inside. And now, because I just stated this fact, I'm going to immediately say that A plus B is less than or equal to the absolute value of A plus the absolute value of B. I'm making both, if anything, larger. And that's it. So now we have the left-hand side is less than or equal to the right-hand side. So we've shown it for case 1. I'm just going to write as desired. Case 2, I'll fit over here. I hope it doesn't get too crowded, but the idea is now, let's continue the proof. Now suppose that a plus b is less than 0. Once again, we are going to be able to compute the absolute value immediately because we have enough information of what we're taking the absolute value of to say how the action of taking the absolute value must follow. All right, consequently, absolute value of a plus b is the negative of a plus b because we have to flip the sign. The computation I'm about to proceed through is not only centered on its own line, but it's actually going to be a multi-line simplification. And when you do that, what I want you to do is freeze the left-hand side and just work down the right and try to line up your equals and your equal signs and your inequality signs so that they're kind of stacked on top of each other. It's just the easiest thing, I think, for a reader to understand. So I'm going to go straight down on the right-hand side and say that, okay, negative a plus b is the same thing as what we would get if we distributed that negative. I'm going to write this as negative a plus negative b. And now I'm going to use the same fact that I've already brought to the reader's attention. Negative a is a real number in its own right, as is negative b. So for each of them, I can say that they are less than or equal to their own absolute values, like that. But the absolute value of negative a is the same thing as the absolute value of a, and likewise for negative b. So we can say equals. And at the risk of being redundant, I'm going to also write as desired, and we're done really, so let's draw a box. Let me step aside for a second to let you read through case 1 and 2. If you need to, you can spend a little time convincing yourself that we've covered all possible scenarios. Like I said, it's possible to do this in multiple cases, but I think this is a really clean approach. Then when I come back, I want to say a few things about formatting here. Just some remarks before we prove this statement again a different way. I want to mention that I believe in being very clear about the structure of your proof. So I announced to the reader in the first sentence that this is going to be a proof by cases, and then I label the cases. I think that's a good habit to get into so that the reader isn't like, wait, why are we now making a different assumption? So help the reader understand the flow of your proof. Unlike in the previous proof where I introduced M, N, J, and K, you might have wondered why I didn't specifically say what A and B were here. And I could have, but they were explicitly defined in the original statement. So I just jumped straight to kind of using them. And that can be okay, again, if what you're working with directly follows how they're being defined. Okay. The other thing I wanted to mention, well, maybe a few more things. You don't necessarily have to include this phrase for this proof to be correct, but sometimes I think, you know, maybe the reader needs a little bit more help to recognize, particularly here, what happened, because it seems like I just threw absolute values on things. So make sure that you don't over-explain easy algebra, but sometimes things that might be like less immediately visible, it's okay to state them explicitly. Several remarks, actually. I used the quantifier here. I used quantifiers in my previous proof as well, some abbreviations. That's the kind of thing I do when I'm writing by hand, as I'm doing on this board, in part to save room. If I were typing this out and writing it a little bit more formally, typically I would actually write for all in words. So some of the abbreviations that I'm using here are conventions I do by hand, but not necessarily what I would write formally. Let's see, for both of these computations, you always want to make sure that your inequalities are preserving one sense of ordering. So here I have equality, here I have less than or equal to, so that the overall flow is that the starting left-hand side is less than or equal to the concluding right-hand side. Here I have equals, equals, less than or equal to, and equals. This is safe as well. It tells me that what I start with is overall less than or equal to what I ended with. Never change directions in this kind of computation. So never have a less than or equal to and then a greater than, never switch directions. So always only move in one direction when you have this kind of inequality that you're working with. Okay, I think the last statement I'll make is that when you have a computation that takes several lines, on scrap paper, you might be working through it backwards, or you might be simplifying both sides at the same time. You might have like little equal signs that you're drawing, or like question marks, trying to figure stuff out. In formal writing, the nicest way to proceed is to get used to fixing the left-hand side and then go down the left-hand or the right-hand side in this case. So left-hand side and then right-hand side, really try to structure a multi-line computation this way. It's easy for the reader to follow the narrative from where we started to where we ended. If you are trying to simplify two sides at the same time, it's much harder to follow. And actually, sometimes it can be done in a way that masks something or something is incorrect. I don't want to go off on a detour here, but really this structure I encourage you to aim for when you have a multi-line computation. I like to call these Oklahoma structures just because they kind of shaped like the state Oklahoma. I apologize to anyone living in Oklahoma. This isn't really what I think your state looks like, but it has the same kind of structure with this like one thing on the left-hand side. All right, I am going to come back in just a moment and I will have erased all of this just about. We will do a second proof of the triangle inequality because our second proof will give us a clue for how to prove this again in a few minutes when we look at the generalized form of the triangle inequality, where the assumption that we're working with real numbers is replaced with vectors in Rn. For the second version of the proof, let me just jump right into it. Proof. Observe that for any real numbers a and b, we find what I'm going to do is take a plus b, this quantity, and square it. I'm going to explicitly square it for the reader. So a plus b squared is, of course, a squared plus 2ab plus b squared. No surprise there. Once again, I have a multi-line computation. I'm going to leave this alone and simplify down the right-hand side, Oklahoma style. And what I'm going to do now is recognize that A and B are both less than or equal to their own absolute values. And in fact, if I take both of these and replace them with their own absolute values, if anything, we will go up in size with this sum. So we have a non-negative number, a non-negative number, something which could actually be negative. I'm going to look at its like positive version. So we're going to go up in size by saying less than or equal to, let me start out by writing a squared plus 2. Here's why it's an inequality. Absolute value of A, absolute value of B. Plus B squared. Okay. I could do what I'm about to do on another line, but let me just also go ahead and say this. So whatever A is, its square is greater than or equal to 0. It's equivalent if we first take the absolute value of A and then square that. Okay. But now if you look at this quadratic expression, it looks exactly like this if what we'd squared was the absolute value of A plus the absolute value of B. What I'm trying to say is that this is the expansion of absolute value of A plus absolute value of B squared. All right, see what you can make of that for just a second. So let me step aside and let you digest this, and then we will come back and wrap this up with one or two more lines. I wanted to give you a chance to see where this is going. If I take the square root of both sides, it's going to look a lot like the triangle inequality. Be careful when you square root this expression, it is not a plus b, because a plus b could be negative. It's the absolute value of a plus b. All right. Uh, I'm going to write here maybe a little bit more about the algebra than necessary, but let me be very specific about what's happening. Taking the square root of both sides, we see what comes out of this. The left-hand side is the absolute value of a plus b. Square root preserves the direction of the inequality here. And then on the right-hand side, I could say the absolute value of the absolute value of a plus the absolute value of b, but I know this to be greater than or equal to 0 because it's the sum of two absolute values. So let me jump straight to this. This is centered on its own line, but I don't really have room to keep going down, so I'll write as desired to the right. Okay, so that wraps up the second proof. You may have liked it more. I think doing it by cases is still a nice exercise, though, because it makes you think about how the absolute value function behaves. Here, this step to this one is really nice, and we'll see that again when we look at the fourth statement. Before we leave the triangle inequality for a few minutes, I want to mention that this inequality is so important because we are often interested in measuring size. And if we're taking the absolute value of something, trying to assess its size, whether it's the size of a number or maybe, as we will in a few minutes, it's like the norm of a vector. Perhaps we don't know too much about whatever this left-hand side is, but we can control the right-hand side. So we often make this kind of replacement where we'll start here and we'll move here. And again, if we're trying to understand size and how big something is, this inequality can give us a way to understand size. So that's why the triangle inequality is so important and why we see it a lot, because it gives us a sense of size and how to estimate one size in terms of the sum of two others. Our fourth exercise will be to generalize the triangle inequality that we just saw for numbers to vector norms. So ultimately, we want to show that for any two vectors x, y from the same Rn, we add them together and compute the length of that, in other words, the norm of x plus y, it is less than or equal to the norm of x plus the norm of y. So you'll notice it looks exactly like the triangle inequality for numbers. If you think over the two proofs that we just did for the triangle inequality, though, the first one doesn't translate to this situation. So we did by cases, thinking about the sign of what we were computing the absolute value of. That doesn't make a lot of sense here when we think about vectors. So this idea of norm here is a little bit different. And instead, let's think over the second approach. Okay, let me do a little bit of scrap work. Let's just see if this is going to check out. We are going to take the length of x plus y. Okay, the length of x plus y is, well, what you could do is think of x and y in coordinates, add those coordinates together, square each one, add those sums, and take the square root. I'm trying to explain what the vector norm looks like in words, but there's a much cleaner way to do this, and that is to recognize that the length of the vector is the square root of that vector dotted with itself. I've omitted vector hats here, but you're welcome to bring them in. All right, and then another option available to us is to say, if possible, let's avoid the square root. So why don't we square both sides? Get rid of this. All right, expand this out. We'll have x dot x. That is the length of x squared. That's good. We see that here. We have two copies of x dot y. And then we have y dot y, which is the length of y squared. Okay, we don't have exactly what we wanted to see because of this middle piece. But remember how I said, any number is less than or equal to its own absolute value, and so we went up in size by making that kind of adjustment? Here, we need to recognize that dot products could be negative. So then it's like, all right, uh, if you want to take a dot product, which could be negative, and go up in size, we could take its absolute value. Oh, sorry, this is just absolute value because x dot y is a scalar. So this is a very similar maneuver to what we did a moment ago when we had the triangle inequality version 2, the second proof we did. And now it's like, well, I want some way to replace this. You can use that cosine formula, the familiar cosine formula for the dot product that comes from, say, law of cosines. I'm actually just going to cite Cauchy-Schwarz, which I put up here. I have a separate video on Cauchy-Schwarz that I will link to in this video's description, but Cauchy-Schwarz will work for us right here. So we will be able to replace the absolute value of x dot y with the product of the length of x and the length of y. Once we've done that, we recognize the same kind of expansion of, say, this side that we had in the previous proof. So that's why I like this exercise. It follows the algebra that we've already done. Now that we've done the scrap work, we're ready to write out a nice formal proof. Let me introduce x and y. So let x, y be elements of Rn. Now we can just, I think, go ahead and do our scrap work computation. We just want to make it part of a nice narrative. So it will be part of a complete sentence. Taking the work we did and making it a complete sentence can be as simple as just dropping the word observe up here. Observe some math. The length of x plus y squared is equal to the dot product of x plus y with itself. Okay, now let's expand. Replacing a number with its absolute value doesn't really need much explanation, so let's just go up in size immediately and make that change. Again, routine algebra doesn't need too much justification unless it's something that looks a little obscure. So this is an immediate increase in the size of the right-hand side. Now we are going to bring in Cauchy-Schwarz. There are a couple ways you could do that. You could say using Cauchy-Schwarz along the way, or we could continue and at the end put where we have used Cauchy-Schwarz. But I'm going to just stop my computation here and say by Cauchy-Schwarz, it's a well-known inequality on vector dot product and norm. The absolute value of x dot y is less than or equal to the length of x times the length of y. Hence, I don't like restarting the right-hand side. So let's go back to the left-hand side. Okay. All right. I need to finish this, but I'm out of room. So what I'm going to do is let you copy this down if you're still working. And then I'm going to just raise this up here. So I'll erase all of this, but it still exists. And I'm just going to slide this line up and we will finish from there. Picking up where we left off, this right-hand side is going to be the length of x plus the length of y squared. And then let me write and therefore. Now just take the square root of both sides. What we have squared is non-negative, so we just immediately square root and we get the inequality that we're looking for. So the magnitude of x plus y is less than or equal to the length of x plus the length of y. We're there, so I will write as desired to wrap up this direct proof. I wanted to do this exercise, A, because the triangle inequality is so important, including its vector form, but also to show you that sometimes you see a result and you think, can I generalize that? So after seeing the triangle inequality on R, meaning for real numbers, you may have wondered, can we generalize this? And the answer is yes. In fact, our second proof illuminated how to proceed. Our final example is from linear algebra, and if you are comfortable working with vectors, please do watch this exercise. The first two examples in this video about the sum of odd numbers and the product of rational numbers involved checking that a definition was being satisfied. In this exercise, what we are going to do is take a definition, namely the definition of a linearly dependent set of vectors, which I will talk about in just one moment. We're going to take that definition and extract a property from it. So this is often a process when we study mathematics, is we define some notion, and then we say, well, what can we start to conclude about items that have this definition? So in particular, imagine that we have a set of k vectors in Rm, and we know that the set of vectors is linearly dependent. The conclusion that we want to extract from that definition is that one of the vectors can be written as a linear combination of the others. So a linear combination is just take the vectors, scale them by numbers, and add them together. Let me just do a quick example over here. Ax plus by. This is a linear combination of the vectors x and y, where here a and b are scalars. Okay, so we want to show that a vector in our set can be written as a linear combination of the other vectors in the set. Let me pause for just a moment, let you read through the definition of linear dependence that I've put up here, and then I will talk you through it. The proof itself is actually fast, and as I've structured here, the beginning of the proof is essentially to state what the definition is telling us about the vectors. So I went ahead and just set up the beginning of the proof. Now that you've had a moment to read through the start of this proof, let me talk you through it. My first sentence is announcing that this object, which is actually a set of vectors, has this property. The property in question is that of linear dependence. We say a set of vectors is linearly dependent if you can find a linear combination of the vectors which equals the zero vector, and which isn't the linear combination 0x1 plus 0x2 plus all the way through 0xk, because that would be a very trivial way to satisfy this equality. So a set of vectors is linearly dependent if there is a non-trivial linear combination of them, which adds up to the zero vector. All right, what we now want to do is show that one of these vectors can be written as a linear combination of the others. Well, if you look at what we have here, we have an interesting linear combination of them. If we could somehow isolate one and say this vector equals the rest by doing just some arithmetic and moving things over, we would show it. I like this example because until you've written this part down, it might not seem immediate how to proceed. So if you just read the statement and you're familiar with linear algebra, you say like, oh, right, I remember that we learned that. And it's sometimes useful when you feel stumped or you're brainstorming to look at the properties you are working with and just cite in words what that property tells you, because sometimes it falls right out of the definition, and that's an example of what we see here. Okay, so we have this linear combination of vectors adding up to 0. We want to isolate one of these vectors and say it equals the rest of them, basically, from this linear combination. We just have to proceed in a way where we make sure that, if our linear combination starts with 0x1, and then the rest of the coefficients are interesting, that we're not trying to isolate x1, because actually that doesn't really appear here on the left-hand side. It's been wiped out by its coefficient of 0. Okay, we know at least one of the coefficients, however, is non-zero. So what I'm going to do next is introduce a phrase. It's called without loss of generality. And for shorthand, we write W log. So without loss of generality means that, you have k choices of coefficients here. It doesn't really matter which one you know to be non-zero, as long as you know at least one of them is non-zero. So I'm going to make a choice, and the choice I make, the specific coefficient I identify, isn't really important because of my ability to kind of treat all of these terms equally. Okay, and let me pause for just one moment, and then we will finish this. Okay, I just had a debate with myself exactly how I want to proceed, and I decided first to be very specific in my choice of coefficients. And if you don't like it, then I will adjust it to be more general, to really feel more general. Okay, so my first attack is going to imagine that C1 itself is non-zero. And again, if you think that's too specific, I will change it at the end. So suppose without loss of generality that C1 is not equal to 0. Now, algebraically imagine solving for x1, the vector that partners with c1 in this linear combination. What you would do is move everything to the other side. That's completely legal. And then you would divide by c1 to isolate x1. And that division by c1 is why it's so key that none of the coefficients is, that at least one of the coefficients is non-zero, so that you can divide by 1. Okay, then x1 equals, and I think what I'll do is I'll just write 1 over c1 out front, and then write the rest of it. I will write one more sentence saying, therefore, x1 has been written as a linear combination of the others, just to go back to the language of the statement. Combo of the others. Okay, I'm going to make an adjustment, but before I do so, let me talk through this idea of generality. Anytime you feel like it doesn't matter which one I pick, the operations involving the elements you're studying should be, say, commutative. Like here I've got addition. It doesn't really matter how I've ordered the vectors in this linear combination. I could be switching them around. I could reorder these vectors. It's a finite set. So anytime you look at this kind of expression, it really should be the case that all of the objects you're studying, they all play the same role in this computation. You always have to be careful if you have something like, I don't know, subtraction, where maybe order matters. Um, so if it's really symmetric in the objects that you're studying, then yes, you can basically grab one. Okay. I would rarely make this specific of a choice. Usually, I think it's normal to just say, CI or C. Yeah, let's just do CI so I can throw a little dot here. All I did was just change x1 to xi so that the reader understands I'm saying here is one coefficient which is not 0. I can do that because at least one of them is non-zero. So this is a specific choice of a coefficient. I'm just not making precise where exactly in this linear combination it occurs. Otherwise, it's the same idea, except here when I write this, I have to maybe not be so specific with my ordering. Sum from j equals 1 through k, j not equal to I. Okay, so basically the sum of all of them except for the ith term. Okay, so with this example, I wanted to show how if you're stumped and you've got a definition, write out what it means. Sometimes just doing that, the act of investigating in words exactly what the definition involves gives you the rest of the proof, because really this line led to the rest of our computation here. I also wanted to talk about this idea of without loss of generality. When you have a nice expression which is, say, symmetric in its variables, you can often reduce the amount of complexity in your proof if you can create this generalized statement. Otherwise, this was just a direct proof. So I showed that from the hypothesis that our set was a linearly dependent set of vectors, we reached the conclusion. That wraps up this video on direct proofs. We have more to talk about, though. We will be looking at, say, proofs by the contrapositive, where you prove the contrapositive statement. We will also do proofs by contradiction and some others.